up being, divide the energy by the number of moles, so it's 99 point, what did I say it was, 427 kilojoules. And then that number of moles is the 3.365 grams divided by the molar mass, which is 46.07. And run that calculation, you find out that there's negative 1.362 kilojoules released in the constant volume process. But for a constant volume process, because no PV work was done, all of that energy was energy associated with the change in the internal energy of the system. And so for delta U, the change in the internal energy system is negative 1.362 kilojoules. Go ahead.
Would it be kilojoules per mole?
Yeah, kilojoules per mole. So the molar quantity bar over it. So point of the message is that constant volume process, no expansion work gets done, all of the energy goes to a change in the internal energy of the system. We calculate this number. Now delta H is equal to delta U plus delta PV. And PV is equal to nRT for gases. And so this delta PV term can be changed to delta N of the gas phase molecules times RT. And we end up going from 3 molecules of gas to 2 molecules of gas. Is that an expansion or a contraction?
Contraction.
Contraction. And so what happens in that contraction is that the outside environment actually does work on us. That work gets dumped off into the environment. And so this term delta nRT ends up being, what does that need to be? Negative 1 times RT. I don't have my calculator with me, so I can't calculate it. And your sum ends up being negative 1,365 kilojoules per mole. So there's a difference in delta H and delta U, and that difference is based on that expansion contraction thing that happens in the system.
So they're both in terms of kilojoule per mole?
Yeah, it's going to be kilojoules per mole. You can take that home and play with it and make it work. I got to warn you, that seems like a really good question to have on an exam. You know, give you a process that happens in a constant volume calorimeter, and then ask you to determine delta H based on that and any change in gas phase molecules. There was a question?
Yeah, do we know the value of T?
Yeah.
Oh, sorry, that was 200. It's just assume, if I don't say something, sorry about that. If I don't say otherwise, assume it's at 25 degrees Celsius, so 298 Kelvin. So usually that's the ambient temperature that we throw in if we don't know the temperature. So we're running out of time, unfortunately. I did want to show you another thing, and I'm not going to get a chance to do it right now. Come to office hours if you want. But let me just explain it to you real quick. So there's a thing called a Carnot cycle. This is going to become important to us when we start to look at entropy changes. And it turns out there's actually a Carnot cycle on your homework set for this section of work. In the Carnot cycle, you have isothermal expansion followed by an adiabatic expansion. And then you have an isothermal compression followed by an adiabatic compression that returns you back to the same state. And for this process, I can ask you a bunch of things. I can ask you for each step what the change in the internal energy of the system is, what the change in the enthalpy of the system is, what is the work and what is the heat, and you need to be able to run those calculations. For the isothermal expansion, we already did this before, you end up, because it's isothermal, having that delta U is equal to 0, and your work is equal to the negative of your heat. So any energy that's expended in expansion is subsequently put back into the thing as heat to keep the temperature constant. And you get a term that looks like this, negative nRT line P final over P initial. The adiabatic one is not as easy. The adiabatic one we started to work on the other day. I had to try to start deriving the relationships for adiabatic processes. I'm going to put some of these relationships, I'm going to make them available on the web so that you can do your homework. But if you set the appropriate conditions for adiabatic processes, which is the Q is 0, and you run the integrations, you end up with the expression that we came up with that says that CV times the natural log of T final over T initial was equal to negative NR times the natural log of V final over V initial. And we said that with the appropriate substitutions, we could turn this into expressions relating to any of the variables, temperature, volume, or pressure. We could stick those in and derive expressions. One of the expressions that you can derive is that T final raised to the CV over R times V final is equal to T initial to the CV over R times V initial. So with this expression, you can figure out on this path what the final temperature is going to be. And once you know what the final temperature is going to be, and you know that it's an ideal gas, you can set delta U to CVDT. So if you want to figure out what the change in the internal energy is during that adiabatic expansion, figure out what the changes are in temperature, and then take what you know about an ideal gas, which is that delta U is only dependent on delta T, and figure out what the delta U is. If I wanted to ask you what the delta H was for that process, you can take that delta H for an ideal gas is Cp dt, and knowing what your relationship between Cv and Cp is, you can derive that relationship. All right, I'll be in office hours in the library if you're into it.